Morning. Few announcements for today. Homework 8 is due this Thursday, as usual. Project 2 was released on Friday. You're going to be working on Project 2 in labs this week. So the checkpoint will be due this Friday, and then the final project will be due November 5th. Also, tutoring starts again this week. If you've signed up for tutoring, please go starting this week. And if you haven't signed up for tutoring, there are still slots available if you'd like to sign up for tutoring. Great resource if you feel like you'd like a little help, or if the midterm didn't go the way you'd hoped. All right, so on Friday, we heard about distributions and center and spread, which gives us an idea of where most of the values are. And today we're going to be looking at the bell-shaped curve and where it shows up in statistics. This is called the normal distribution. And on Wednesday, looking ahead, we'll apply that to looking at the sample average and how much variability it has, and how accurate that is as an estimate of the population average. Okay, so a little review from Friday. We talked on Friday about standard units, which are a way of converting numbers to be in a standard form, normalizing them. And standard units compute how far above the mean or below the mean a value is. And the way we measure how far is in terms of the number of standard deviations. So this is often called a z-score, represented by the variable z. And it's obtained, you subtract off the mean, and then you divide by the standard deviation. So if what you got from this was 1 in standard units, that corresponds to a value that is larger than the mean. It's larger than the mean by 1 standard deviation. In other words, it corresponds to a value that's equal to the mean plus 1 times the standard deviation of the distribution. So negative values in standard units mean a value that's smaller than the average. Positive values mean a value that's higher than the average, and a 0 means a value that's equal to the average. So for instance, if you were looking at exam scores, this would be a way to compare yourself relative to others in the class. Positive means you're doing better than the average. Negative means you're doing worse than the average. And this is scaled in a way so that you can interpret how much better than the average you're doing. Because sometimes you might have an exam where the average is 70 and there's very little variability around 70. Most people got between 65 to 75. Those would have a small standard deviation. Sometimes you might have an exam that the average is 70, but there's a lot of variability. The scores range between 40 to 100. That would have a large standard deviation. So you can't really compare a score of 60 on those two exams, but you could compare if you put them in standard units. So those are standard units. Let's talk about the standard units and the standard deviation and the histogram. If you have a histogram of some data, typically you can tell where the average is. You look about the center, or where, if that was a bunch of weight, where the balance point would be. But it's often not so easy to just look at a histogram and estimate where how large the standard deviation is. That can be a little hard to tell by your eye. Unless, in one special case, if the histogram has a bell shape. If it's this bell-shaped curve, then there is a way that you can eyeball the histogram and get a pretty good idea of what the standard deviation will be. And the bell-shaped curve has a particular relevance and importance in statistics. So we're going to talk more about that later on in this lecture. Okay, so here's a rule of thumb for eyeballing the standard deviation if you have a bell-shaped curve. If the histogram is bell-shaped, then the average is at the center. The highest part of the bell is the average. And the standard deviation is the distance between that average, that center, and the points of inflection on either side. And what do I mean by points of inflection? By points of inflection, what I mean is if you were to draw a smooth line over the bell, over the histogram, this smooth bell shape over the histogram, you'd see there's some ranges where that line is forming a bell with the inside. In other words, like a teacup turned upside down. And there are some regions where it's forming like this. It's like it's opening to the sky like a satellite dish. And the point of inflection is the point in between where it switches between those two. Okay, so it's right here between the red and the yellow. So if you have a bell-shaped curve, you can often get a sense of what the standard deviation is. In this case, the mean, the average is right at the center, which is, I guess, about 64. And you can see this point of inflection is about, what would you call that? 66.5. So the standard deviation is between 64 to 66.5. So call that about 2.5 for this example curve. Yeah, you can think of this as where it switches from concave to convex. That's the point of inflection. Let's do a little demo so you can see what that looks like. Okay, so here we have the weights of babies at time of birth, and we're also have information about the mothers, and we're going to look at a histogram of the heights of the mothers. So this is reflective probably of the heights of women in general among society, at least of childbearing age. And here you can see a histogram of those heights of all the mothers. Okay, so you can see in this shape of this histogram, it looks kind of like there's a bell curve that could be superimposed on top of this histogram. So that tells you that you could use this rule of thumb to try to visually estimate the mean and standard deviation. Where do you think the mean height of mothers is based on this histogram? Give me a number. Go ahead and type in chat what you think the mean is. $64 looks pretty good to me. It's right around the peak of this histogram, which is somewhere, if you can see my cursor, somewhere around here. And if we go down to the x-axis, that looks like it's around here, 2/3 of the way from 62 to 65. That looks like about 64. Could be a little higher, could be 64.5, maybe could be a little less, but that's roughly what the average is. And if we look for the standard deviation, we can see here, we kind of have an upside down teacup and then a satellite. And the switching point looks like it's at around, point of inflection at around, I don't know, what would you say, 67.5, 67-ish, something like that. So the distance between the mean of 64 and that 67-ish is about 3.5, something like that. All right, so let's compute what the actual answer is since we actually have the numbers. And here we see the mean is 64. We got that just right. And the SD was about 2.5, so I was a little too high. So it really should have been from 64 to 66.5. So I guess I misestimated the inflection point. All right, so not a big deal. Don't have to stress over this rule of thumb. Just gives you an idea of what the standard deviation is telling us when you have a bell-shaped curve. It's telling you roughly the width of the bell. Typically in practice, you'll have all the numbers and then you can actually compute the standard deviation. You don't need to eyeball it from the histogram. But in this case, you can see that this range between mean -1 standard deviation and mean +1 standard deviation, that's from about 61.5 to about 66.5, is centered around the mean and constitutes a large fraction of the area or the bulk of this histogram. So that gives you an idea that many of the values of many of the heights of the mothers are going to be between 61.5 to 66.5 inches high. In other words, 5'1.5" to 5'6.5". Okay, so don't stress out too much about finding exactly the point of inflection on the visual graph. I'm just trying to give you some intuition here. All right, so a bell-shaped curve is so important in statistics that it has a name. And in fact, the typical name for it is the normal distribution. Why normal? Because it's so common that statisticians of old called it normal to see. Now, there's some beautiful mathematics behind it. There is an equation for the shape of this bell-shaped curve that's kind of beautiful because it relates e and pi and 2 and these mathematical constants that you wouldn't think have any relevance, but you don't need to know that for this class, and we're not going to use it. What's relevant to you is that the shape of the normal curve, the standard normal curve, looks like this. You can see why it's called a bell-shaped curve. And the standard normal distribution is a normal distribution that has a mean of 0 and a standard deviation of 1. Okay. You can also have normal distributions that have a mean other than 0 and a standard deviation other than 1, but the standard normal has mean of 0 and standard deviation 1. We can see how the shape of this curve resembles the histogram that we had of maternal heights. And we're going to see in a little bit later in this lecture why this distribution is fairly common. To give you a little bit of an intuition, roughly speaking, it happens when you add up a bunch of small components to get the observed data. This is very crude intuition, but you can think of your height as being determined by hundreds of genes. Each gene might make you a little taller or a little shorter. So you can think of your height as being the sum of all those contributions from all of those genes. So that final number, the final height of me or any one person, is the sum of a bunch of contributions. On an exam, it's common for exams to have more or less looking like a normal distribution. Not always, but it's a common thing to see. And some intuition for why that might happen is for each question, you can either get some points or not. So your total score is like the sum of the scores on all the parts. And it turns out when you obtain a number in that way, you often end up with something that has more or less a normal distribution. Normal distributions are very convenient because if you know the mean and the standard deviation, you know everything there is to know about a normal distribution. And in particular, you can figure out where most of the data will lie if you have a normal distribution and you know the standard deviation. So last lecture on Friday, you saw Chebyshev's rule, which was some motivation for why the standard deviation is a useful concept. Chebyshev's law tells you that no matter the distribution, most of the data is near the average, where by near, I mean within plus or minus a few multiples of the standard deviation, like between average -3 standard deviations and average +3 standard deviations. Many of the values will be in that range. That's true no matter what distribution you have, whether it's a normal distribution or something else. But if you have a normal distribution, if you have a bell-shaped curve to your histogram, then we can be a lot more descriptive. Then we know not just that most or a large fraction of the data will be in that range, but almost all of the data will be within plus or minus 3 standard deviations of the norm. They'll be between average minus 3 times standard deviation up to average plus 3 times standard deviation. Okay, so let me give you a visualization. Here is a picture of the standard normal curve. This is a bell shape. If you have a histogram whose shape more or less approximates this bell shape, maybe you have a normal distribution. So let's suppose you've got a normal distribution, the shape like this. We can look at how many values are within 2 standard deviations of the mean. What do I mean by within 2 standard deviations of the mean? When I say that, that's a way of saying how many of the values are larger than the average minus 2 times the standard deviation and smaller than the average plus 2 times the standard deviation. If you were to convert all of your values to standard units, another way of saying that is how many of the values in standard units are between -2 to +2. And the answer for the normal distribution is about 95% of the values will be between -2 and +2 in standard units. Okay. So if the score on the midterm had a normal distribution, and I told you the mean and the standard deviation, then it would follow that 95% of the class are getting a score that's between the mean minus 2 standard deviations and the mean plus 2 standard deviations. There are a handful of people in these blue areas that are even lower, that are more than 2 standard deviations below the mean. And there are a handful in this blue area that's higher than 2 standard deviations above the mean. But it's only about 5% of the area is in the blue and 95% is in the yellow. This is going to be useful. This is not why we use 95% confidence intervals, but when you want to create a 95% confidence interval, this fact's going to be useful. So remember this for later. Why do we use 95% confidence intervals? That's pretty arbitrary. It's an arbitrary convention. Remember what Fisher had to say? It's arbitrary what your p-value cutoff is, but I happen to find it convenient to use 5%. And then the whole world started using 5% as if it was some great rule that everyone should follow. That 5% cutoff corresponds to a 95% confidence interval. And just like many people started to follow that convention of a 5% cutoff, many people follow the convention of 95% confidence intervals. Okay, so let me show you a little bit about where the normal distribution comes from. In this class, the most common case where we're going to see the normal distribution is when we take samples, take a sample, and we compute the average of values in that sample. All right. So if we do that, if we take a sample and then we compute the average of the numbers for our sample, that average is called a sample average. We call it a sample average to distinguish that from the average of all the values in the population. The average of all the values in the population is called a population average. Okay. So if I took all the mothers in the US, the average of their heights would be a population average. If I took a random sample of 100 mothers from the US and took the average age of the mothers in my sample, that would be a sample average. Why do you think we compute sample averages? Why are we interested in sample averages? Anyone want to try any thoughts on that in the chat? They're important. Why are they important? Can't always get the data for the whole population. So we're forced to only work with a sample. Yeah, maybe I want to know what the population average is. I can't get the whole population. I can only get a sample. Then the sample average might be useful as an estimate for the population average. So we care a lot about sample averages and what the properties of sample averages are. Because we do this a lot in statistics. We do some sampling and then we try to draw some conclusions about the whole population based on our sample. Great. Okay, so when you look at sample averages, something really interesting happens. When you get sample averages, we start to see a particular shape tend to show up over and over again across many different applications and many different data sets. And this something called the central limit theorem tells us, gives us a prediction, gives us actually a mathematical formula for what will happen. It says that sample averages are connected to bell-shaped curves. I want to give you the chance to discover for yourself the central limit theorem, and in particular, what's going on with sample averages and bell-shaped curves. So I'm going to work with a data set. I'm going to take the data set we had before of flight delays. Remember this? This was 13,000 flights out of San Francisco from several years ago. This case, we had the entire population of data. Usually we won't, but in this example we did, and then we're gonna that's gonna enable us to do things like simulate what would happen if we drew a sample from the population. Now let's look at the distribution, the histogram of flight delays for these flights out of San Francisco. What does a negative delay mean? That means the plane departed early, ahead of its scheduled time. Okay, so you notice there are a few flights with a negative number for the delay, but most of the delays are positive. And the shape of this curve, you can see that most delays are fairly small, but there are a handful of flights that were delayed a really long time, like several hours. Does this have a bell shape? In other words, does this look like a normal distribution to you? No, no. So this is not, these flight delays do not have a normal distribution. And that's common for data in a population, that the data in the population may have annual distribution, not necessarily a normal distribution. You can still compute the mean and the standard deviation, even though it's not a normal distribution. So we can see the mean flight delay with our God's eye view of all the data. The mean is 16 minutes and the standard deviation is 39 minutes. But in practice, we wouldn't be able to compute that because we wouldn't have the entire population of data. This is just something we can do with this data set that we are using for pedagogical purposes. Can also see that in this case, most flight delays are small. The median delay is 2 minutes, but there's a handful of very large delays that are skewing the average. Okay, so what I'm now going to do is I'm going to simulate the process of drawing a random sample from this population. We're going to take a random sample of flights. And then for the flights in that sample, we're going to compute the average delay of the flights in this sample. Okay, so this code here, you can see I've defined a function that takes a sample from the population of some given size. And then we get the delays for those flights, and we compute the average. And here I have run this process once to get a sample, and the average flight delay in that sample was 19.47. I could get another 100 flights sampled at random. And in that sample, the average delay was 15. And here's another one where the average in this third sample was about 19. So I could keep generating more and more samples and compute the mean delay of each of those samples. Now it was about 16 for this fourth sample. Okay, so maybe this is giving me some idea about what I might expect to see for the sample average. Notice that there's some randomness in which flights got chosen. So the sample average is not the same every time. It depends on the sample, which depends on those random choices. That means there's some variability in the sample average. You can see that it's sort of somewhat similar to the population average. The population average was 16.7, and some of these are a bit larger than 16.7, and some are a bit smaller than 16.7, but they're in the ballpark. So now you might wonder, if we took a lot of samples and we took the sample average for each of those and looked at the distribution, what would that distribution look like? So that's what I'm going to do next, is I'm going to repeat this process, but now not 3 or 4 times. I'm going to repeat it a whole bunch of times. I'm going to collect all of those sample averages from each of those samples. And then I'm going to display a histogram of them to look at the distribution of the sample averages. So I wrote some code to do that. And I'm going to run this code in a minute to generate the distribution. But before I do, a quick question. The distribution of sample averages should have about the same shape as this histogram here, true or false? False, yeah, not necessarily. The values in the sample will have about the same distribution, about the same shape. But now we're taking an average. So who knows what shape that'll have? Not necessarily the same shape as the values in the population. Because here we're histogramming not the numbers in the sample, but the means of the numbers in the sample. And that's going to turn out to make an important difference. So let's run this code once. It'll take a while. My computer's chugging away, generating 10,000 simulated samples and the average of each, and then histogramming all those numbers. And we can look at all of those numbers here. So here's an array with 10,000 numbers corresponding to 10,000 samples. And you can get a sense of the sample averages that are showing up in this way. There's 10,000 numbers in there corresponding to the 10,000 samples. So let's histogram that. I'm going to put that into a table so that I can use the hist method to draw a histogram. And we get a histogram that looks like this. Does this look like a bell shape to you? Yeah, approximately. It's a little bit of a leaning bell, but it basically looks pretty close to a bell shape. Where is this bell shape centered? Let's see, 15 is this grid line right here. The center is somewhere around the peak, which is just a little bit to the right of that grid line for 15. So maybe we're talking 15 and a half, maybe we're talking 16, something like that. Maybe it could be even a little bit higher than 16 because of the slight lean to this bell. Okay, so that's kind of interesting. You can compare that to the population average was 16.7. The population average looks like it's very close to the center of this bell shape. Where, in a moment, I'm going to ask you to maybe estimate for me the standard deviation of this distribution. But before I do, let me note something here. The distribution of the population data was not a bell shape, right? The distribution of numbers in the sample, delays in the sample, also not a bell shape. It'll have approximately this curve. But the distribution of the means of all the samples does have a bell shape. It's kind of a different sort of thing because this is now not a distribution of values in one sample. It has to do with looking at many samples and a derived number that's derived from the sample. Now, I'm wondering what happens if we were to generate a sample size of a different size. Here, I generated a sample of 100 flights. Suppose that I did this with more flights, let's say 400 flights. Let's do the same thing here, but now with a sample size that's larger. Now each sample has 400 flights in it. As before, I'm generating lots and lots of samples, 10,000 samples, but now each sample has more flights in it. Then for each sample, I'm going to compute the mean delay in that sample, and I'm going to visualize those. So let's run that, let the computer chug, and let's look at the shape of this. Maybe just form in your mind a guess for what you think the shape might look like. And think about whether it's something like this shape, something different. How is it similar? How is it likely to be different? And now we can see what the result is. Does that look like a bell curve to you? That looks like a bell curve to me. Now we don't even have much of a lean to this bell. Okay, so we have a bell shape. Where would the center of this bell shape be? Looks like about almost halfway between these two grid lines, but maybe a little bit to the right of that. So a little bit to the right of 16.25, maybe 16 point something. I don't know, 16.5 looks plausible. You can see how that's very similar to the population average. How would you compare these two distributions? The distribution of sample means and the distribution of sample means for samples of 100 versus samples of 400. Maybe I should shrink this a little bit so you can see them on the same screen. Talked about one way they're similar. They both have kind of a bell shape. Another way they're similar is they're both centered at more or less 16 and a half, the population mean. What's a way that they look different? The x-axis is different. Yeah. Visually, they look quite similar. But when you look at the x-axis, you can see that the range of values is much narrower for the bottom graph than the top graph. In the top graph, when we had samples of 100, the values were ranging from, let's say, 10 to 25 or or 12 to 22. When you had the bottom graph with samples of size 400, the values are ranging now from maybe like 13 to 20 or 14 to 19 or something like that. So in terms of what way it shows up on the screen, they both look to the eye like they have about the same width. But when you look at the x-axis, you'll see that the width of the bottom graph is actually substantially narrower. How could we quantify that? How could we put some numbers on that? How could we measure that? The standard deviation. Yeah, the standard deviation is a measure of the width of the normal curve. These both look like approximately a normal distribution. We could measure their width using the standard deviation. So let's try to do that. Well, we could try to estimate their width visually based on looking for the inflection point. And I think I might get something like 12.5 to 16.5. So I might get something like 4 for the top picture, but we have all the values. So let's just compute the standard deviation. The answer is a standard deviation of 4 for the top histogram. And for the bottom histogram, standard deviation of a little less than 2. Okay, so the bottom graph is narrower, about 2 times narrower than the top graph. And we can measure that with numbers. What are the implications of that? This narrower means that the data is more clumped around the middle. It's more clumped around 16.5. The sample means are closer to 16.5 when you have a sample size of 400 than when you have a sample size of 100. What does that mean for our estimate if we're using the sample mean to estimate the population mean? Is it good or bad or just sort of irrelevant if they're clumped around the population mean? More clumped is better. Clumped is good. The estimate is more accurate. Yeah, clumped means the sample means are closer to 16.5. They're closer to the population average, the true value that we don't, in practice, we won't know that we're trying to estimate. Clumped is good. Clumped is mean my estimate is more accurate. So you can see that as we increased the sample size, the shape of the histogram stayed pretty similar. The center of the histogram stayed pretty similar, but the data got more clumped, which means that our estimate got more accurate. How much more accurate? It got about 2 times more accurate. It got 2 times more clumped, as measured by the standard deviation being 2 times smaller. Now, here's the awesome part. You're going to get a chance to discover for yourself the central limit theorem. I want you to make a prediction for me about what you think will happen if I take a sample size of 900. While the computer is generating for this, tell me what you think this picture is going to look like. What's going to be the same? What's going to be different? All right, I see lots of predictions. Same shape, bell curve, but the standard deviation will be smaller. The bell will be even narrower. The data will be more clumped. Let me see if I can make you be more specific in your predictions. Those are great predictions. I want to see if you can quantify for me how more clumped you think it's going to be. In other words, how small you think the SD is going to be. What do you think the SD is going to be when I show you this picture and I compute the SD for a sample size of 900? Any ideas? Let's check it out. Let's see what happens. Bell shape. Is this narrower? Yep, it's narrower. Now we're looking at values from like 15 to 19, so like an even smaller range. Check if the standard deviation got even smaller. Yep, even smaller. It's 1.3. Got closer to 1. Yeah, that's true. The standard deviation got even smaller. All right, let's see if I can help you a little more. There's a pattern here to be found, and I am hoping that we can discover the pattern together. I'm now going to choose a sample size of 1600. And I'm going to do the same things we just did before, but now for a sample size of 1600. So I did it for 100, 400, 900, and now I'm doing it for 1600. Natural prediction is we're again going to get a bell curve. Probably it's going to be even more clumped. The SD is going to be even smaller, but how much smaller? See if you can make a guess for what you think the SD will be for a sample size of 1600 based on what you've seen so far. You don't need to type it into the chat. And let's take a look at what results we get. I see a range of guesses. I love it. I love it. This is a great learning method. Form a prediction about what you think you're going to see and then test your prediction. This is going to help us find a pattern here. All right, my computer's chugging. It's chugging really hard. That's a great question. I love your question. Is the SD a linear function of the sample size? Let's find out. Let's see. You're asking exactly the kind of question I'm hoping you'll ask. Hopefully, I'm giving you enough data points here that we could try to figure that out. All right, bell curve again, even narrower still. SD got even smaller. SD is a bit less than 1. All right, do we think the SD here is a linear function of the sample size? With 100, you had an SD of just under 4. With 400, you had an SD of just under 2. With 900, it was just under 1.3. With 1600, it was just under 1. Is that linear? Doesn't seem linear, right? Here we increased the sample size from 100 to 400. That we increased the sample size by a factor of 4, but our SD got smaller by a factor of 2. Not linear. Then I increased the sample size by another factor of 4, from 400 to 1600, and I went from a little under 2 to a little under 1. Again, a reduction in the SD by a factor of 2. So it looks like every time I increased the sample size by a factor of 4, my SD decreased by a factor of 2. What about when I increased my sample size by a factor of 9, from 100 to 900? My sample size increased by a factor of 9, and I went from 3.9 to 1.3. What ratio was that? That was a ratio of about 3-fold reduction in SD. Increase the sample size by a factor of 9, SD reduces by a factor of 3. So I see you typing in the chat. Maybe you found the pattern. The SD is decreasing as you increase the sample size, but not linearly. It goes by the square root factor. It goes by a square root factor, the square root of the sample size. All right, so this now is the central limit theorem. Good job. Central limit theorem now says, in general, if you take a sample and the sample is large and is drawn at random with replacement, we drew samples with replacement in this example, then no matter what the population distribution is, the distribution of the population doesn't have to be normal. It could be some crazy thing. Regardless what the distribution of the values in the population is, the distribution of the sample means, of the numbers in the samples that you obtain in this way, that distribution of sample means is roughly normal. It's going to have a bell shape. And you discovered the rule of thumb for what that normal distribution looks like. A normal distribution is specified by its mean and by its SD. What's the mean of this distribution of sample means? Where is it centered at? We saw in this example, the center was about at the population mean. And what is the SD? We saw in this example that the SD is related to the sample size. The larger the sample size, the smaller the SD. It goes down by about a square root factor. In next lecture, we're going to see the exact formula. But for now, the interpretation of this is that when you have sample means, a larger sample is better because it's giving you a more accurate estimate. Last, I want to comment on one question I saw. I saw a question, how does this relate to the law of averages? Remember what the law of averages says. The law of averages says, if you take the average of the numbers in the sample, then that will be similar to the population average. And it's more similar the larger your sample size. So the law of averages is talking about where the center of this distribution is. It's saying it's centered at the population mean. The central limit theorem includes that statement and also tells you that the distribution is normal, is roughly normal. And as we'll see next lecture, also enables you to predict what the SD of this will be. All right, so this has a crucial relevance for any time we use the sample mean to estimate the population mean. We'll see more on Wednesday. Thank you for joining with me in helping us all discover together the central limit theorem. See you Wednesday.